and then I will kind of give you an introduction. How would we go ahead and compute various scattering amplitudes? I promised I'd use that, but we didn't.
Thanks for asking.
No, I actually, okay, so that's something that I want to ask you. So what I can have another lecture, and I was thinking of having another last lecture on 17th, okay? And the last lecture I will talk about T-duality and toroidal compactification. So that what you guys want to hear? Okay. So right. So that's and let's do that. Okay. And right. And so once you're done with your homework assignment, just bring it in and put it in my mail. All right, guys. So let's go ahead and. Right. So what we have been studying for some time, we have been studying a path integral, right? So follicle path integral. We studied it in flat space-time. We generalized it to strings propagating in curved space-time. And so this partition function takes the following form: so dx dg, and then we have to divide by the volume of a diffeomorphic group and a volume of Y group, right? So those are reparametrization invariants on the wall sheet. And then we have e to the minus s, the Polyakov action for the x field. And then we have a dilaton, what we know expectation value of a dilaton times the Euler character. And so this is a partition function. And then we can go ahead and insert various vertex operators and study string scattering. Okay, so what we discussed a lot about various types of world sheets and cross-caps and homogeneous surfaces. So what I want to talk now is some subtlety which involved in fixing this gauge symmetry on the world sheet diffeomorphic times wild. Okay, so what we're going to talk now is, and that will introduce the idea of moduli. How do moduli show up in string theory? And then we will learn about conformal killing vectors. Okay, so what we're going to do, we're going to consider subtleties in fixing differ cross Y, right? So remember the way how we set up our computation is that in order not to overcount, we have to integrate along the orbits, which are in some sense orthogonal to the gauge transformation, right? So this is a gauge slice. And then we have to perform an integral so that our orbit of integration intersects each gauge slice only once. And then we said that generically, what that means that what we have to do, we have to fix metric, right? So fixing, and remember that we discussed this gauge fixing. We introduced the idea of four-fold ghosts, and then that led us to the idea of critical dimension, right? So something that we made, that we mentioned is that fixing this gauge, the same as fixing the wall sheet metric. Right, and so we were fixing this wall sheet metric to particular, we were working in a conformal gauge. Just one second, let me finish. And so in particular, so the wall sheet metric has three independent components, right? Three components. And so what we notice that there are precisely three reparametrization degrees of freedom, right? So we can reparameterize coordinates on the wall sheet, right? And so that gives us two And then we also have one additional degree of freedom associated with a while rescaling plus while transformation. So GAB goes e to the 2 omega GAB. Okay, and so the point was that the number here is also 3. So we have 3 arbitrary functions, and we can use that to actually fix the 3 arbitrary functions on the wall-shaped metric and put it in any form we want. Yes?
Because the if this slice is just a section in the fiber bundle of the base group.
But okay, so let's don't use this complicated language. So again, the idea is very simple, right? So we have a Polyakov action, and the Polyakov action has huge symmetries, right? And so, some of the symmetries are local symmetries, which are diffeomorphism invariants and while invariants, right? And so when we compute our path integral, we have to compute over inequivalent field configuration, right? And so what that amounts to dividing by, if I choose, so if I choose my field configuration here, then moving along a gauge slice means that for this particular field configuration, what I do, I act with a diffeomorphism while transformation. Let's keep it the way I like that. Okay? All right, guys? So what we're going to do now, we're going to actually discuss this 3 equals 3, and we will find out that it's not, there is some subtlety associated with that, and that the subtleties goes both ways, okay? And that leads to important consequences. All right. So again, in order to understand better what's going on, so let's go back to an example of a point particle. Right? And so in this case, so we have an action, point particle, which is given by the following path integral. So I have to integrate over a metric on the world line of a particle. So I call it GE, right? So it has one component. And then I have an action, a world line action for a point particle. So x minus 1, x dot mu, x dot mu plus m squared. I need the math, but we can always turn off the math. Okay, and so what we're going to do now, we're going to look at configurations in the field space which are closed, right? So we're going to consider paths which is a closed loop. Okay. So what this means, so I can assume that my parameter tau changes from 0 to 1. Okay, and so the fact that I'm considering field configurations which are periodic simply means that x mu of tau plus 1, I have to identify with x mu tau in the same with the head rate on the world line. Okay. Good. And so now the idea of kind of going repeating the same argument. So we have one metric component, right, E of tau. So one metric component. And then we have a single reparametrization invariance, right? So we can redefine. I can redefine my coordinate tau, right? So tau goes to tau tilde, which is a function of tau. So one reparametrization. And so in particular, I know exactly how does my metric transform once I do this reparameterization of the world line coordinate. So I know that E tilde, D tau tilde must be equal to E d tau. And so in particular, it appears that I can make a gauge choice, right? So I can fix a metric, much like we did in the case of Walshed for a string, right? So we fix the metric to be flat on the Walshed. So here what I can do, I can kind of do an analogous thing, and I can use the reparameterization freedom in order to fix my metric to be unity, right? So this is gauge fixing. Gauge fixing. And so, so that's kind of the starting point after which we went ahead and explained all these Fourier-Popov determinants and went from there on. And so now what we want to do, we actually want to see whether what we're calling here gauge fixing, whether that's indeed a complete gauge fixing, and there is nothing nothing strange going with this. And in fact, it does. So there are two types of complications. So let's discuss them. So the first one is complication one. Okay. And so yeah, sure. So we fix the metric in this way. So what this implies, it implies that d tau tilde equals to E d tau. And so I know what's my new world line parameter. So tau tilde is simply given by an integral from 0 to tau, and then I have d tau double prime d of tau double prime. However, previously what we had that the range of integration tau was from 0 to 1. And so here we can ask the question. So we have this new parameter in this gauge fixed metric. What is the range of variation of this parameter, right? So clearly it goes from 0, right? So we set tau tilde equals to 0 when tau equals to 0. But tau tilde of 1 is given by the integral. And in fact, this number is not always equals to 1, okay? So what we are computing here, we're computing the invariance length of a circle, right? So remember that our configuration, well, our world line has a topology of a circle. And so, evaluating this integral, what we are doing, we're just computing the length of this circle. Okay? And well, this length of a circle can be anything. It doesn't necessarily have to be 1. So, so what we are discovering with you right now is that we cannot simultaneously choose a gauge in which the metric is 1, and then keep the coordinate range to be the same, right? So we cannot simultaneously set the metric to be unity, right? And moreover, there is a physical, well, in this case, there is a geometrical meaning to this range of coordinates, right? So that's in this gauge fixed metric, which just gives us the invariant length of a circle. So what we can do, so we can, so we have two choices, right? So one choice, what we can do, we can fix the metric to be equal to L, right? And so if we do that, so that guarantees that tau prime, right? So our new gauge fixed coordinate will change from 0 to 1. So we preserve the range, right? Or the second, what we can do, so we can keep, we can indeed keep the metric gauge fixed to 1, but so I have to put n here, right? But the price we will pay now is that our coordinate will be ranging from 0 to 12. In either way, there is one leftover unfixed parameter. Yeah, so I use prime. All right, so what we are finding is that even though we have one gauge degree of freedom and we have one reparametrization invariant, so we cannot completely gauge fixed metrics. So in other words, there are inequivalent classes of metrics, right? And so those inequivalent classes of metrics in this particular case is parameterized by a single number, right? So that's an invariant length of a circle. So what we are finding is that fixing gauge symmetry does not identify all tetra. And so what this implies that we have a one parameter family of inequivalent metrics, okay? Well, I can fix a metric, I can fix a metric, but then I'm left with the modulus, right? So this L, this or, if you wish, I can fix a metric. Either way, I can put, so this one parameter, that's our first encounter with the moduli. And so what we are doing when we are computing a path integral, right? So we have to evaluate the path integral over all inequivalent configuration of our fields.
And let the tau to be 0 to 1/2.
What does that imply?
So that's another.
I mean, this is the way, so what you are saying is that you're telling me that there is a modulus, I'm telling you there is one parameter modulus space, you are agreeing with me, and all you are saying is that, I'm just put a different coordinate on this modulus space. What's important here is, in fact, how many, again, it's like, you have a space that parameterizes you in equivalent metrics, and you can parameterize this space in different ways. Right? So of course you can do that. Right? But, and in fact, there is it's actually a good question because, well, there is, I don't have time to go into the details, but typically these moduli spaces, they have very beautiful properties. Right? And, but again, they are, well, okay, so what I wanted to say, the physical thing is that in this path integral, by definition, we have to integrate over inequivalent configurations, right? So, so even though what we can do, we can gauge fix the metric to be 1, but we will still have to integrate over this parameter L. Okay, so there will be one out of all possible, so here we have to integrate over all possible metrics, right, over all possible functions E of tau, and out of that infinite functional space, right, there is an only single integral left. That's an integral over GL. That's an inequivalent space of metrics. Okay? Yep.
tau, for example, so it will be a function. So
Yeah,
when you
again,
choose only one.
Yeah, so as you can, again, this is kind of going along the same lines. So as you can see, what is a physical statement is that, again, you have to think in terms of inequivalent configurations. And we're finding that there is a single parameter that describes inequivalent configurations. Now, how do you introduce that parameter? It's up to you. So here I said that I introduce it in a metric, but I don't introduce it in a coordinate range. Or I introduce it in a coordinate range, but I don't introduce it in a metric. But of course, there is an infinite set of possibilities in between, right? But it will still not change the fact. The fact will still remain that the parameter space of inequivalent metrics, right? So we have a metric on this world line. So there is a coordinate tau, and there is a metric, right? E as a function of tau. And so using reparameterization invariance, I can fix it to particular function wherever I like, but there will be still always one unfixed, so my metric will have a label, a physical label, and that physical label is L. Okay. So this label L simply corresponds to a length, right, of my world line. And from this perspective, it's clear that there is nothing by changing variables. You can never remove it because it's a geometrical object. It's an invariant length of a world line, and there is no change of variables that can change the length. Right? Well, here we're not having wild transformation, right? So at this stage, we're talking about particles, right? So we'll talk about voltage, but the idea is simply to introduce here. Okay. So any more questions, guys? All right. Okay, so as I was saying, so this L, and by the way, so that's like measure 0 on all possible space of metrics, right? Again, I was saying that you start with an arbitrary function, the metric was an arbitrary function that enters in that integral, and now the only thing that physically inequivalent metrics are parameterized by a single parameter. It's not a single function, it's a single parameter. So this L is an example of a modulus. Okay. So what will happen? So let me say a few words. So because most of the discussion today will be a bit mathematical, and I don't want to lose physics. So what will happen? Remember that that we evaluate this path integral, right? And in principle, there will be conformal anomalies, right? And so in order to require that our string theory is invariant under wild transformations, so that leads to vanishing of the beta functions, right, corresponding to wild transformations. And vanishing of the beta function produced for us equations of motion for the field, right, that live on the wall sheet. So in this case, those are like a field. Well, so this is analog of X, right? So you might ask me, so how does the moduli will show up? Well, so the moduli will show up again in these beta functions. Okay, they will show up in these beta functions, and they will have their own equation of motion. And you can then ask, how does that will factor into the effective action? So what will happen is that those guys will have an effective action. They will look like scalar fields, okay? And moreover, they will look like a massless scalar field. So this will be a generic, so when we, next time when we talk about toroidal compactifications, right? So then we can probably discuss more of these issues. But one of the things that will happen when you try to build up some realistic scenario in string theory is that there will be a lot of these moduli. a lot of massless fields. Okay, and you can see from this simple example where does moduli show up. All right, so I said there are two complications. One complication is that there are inequivalent classes of metrics, right, in general. But then there is another complication. And so this complication too goes the other way around. So when we fix a metric, we don't necessarily fix all symmetry. So in this case, we don't necessarily fix all possible diffeomorphisms on a world line. Okay, so complication two is that not all gauge symmetries are fixed by choosing a fiducial metric. Right. So this example, what we are doing here. So this is our choice of a fiducial metric. So choice of remember, that's exactly what we did in string. So we chose metric to some particular gauge fixed form. Later, we have to verify whether the choice is independent after gauge reparameterization, right? So the subtlety here is that once you choose this fiducial metric and you are thinking you fix all possible diffeomorphic transformations, that's not always the case. And an example here is that so when I choose my fiducial metric to be a constant, right, either as in the first case or in the second case, so there is still a leftover reparameterization and so those are when tau goes to tau tilde as a function of tau, and that's just tau tilde plus a fixed shift, right? So of course you can see that that saying such a shift will have no effect on my tetrate, so there is a residual gauge transformation left after I fix symmetry, right? So E tilde equals E, and so it's unchanged. Right. So what we are finding that there are two types of mismatches when we do all the gauge fixes. So and so by the way, so the leftover unfixed parameters in gauge symmetries are referred to as conformal Killing vectors. Well, okay, we'll call them conformal Killing vectors in the case of Bolshevik string. So we see in general, so we see two types of mismatches. Okay. So with the number right. So when we try to match number of metric parameters equals to number of local gauge symmetries. And so those mismatches are, again, so there exists inequivalent metrics. And so those are the guys that look for moduli, and I'm going to call them, I'm going to denote them by mu. So mu is the number that tells us how many, what is the dimensionality of the parameter space that describes inequivalent metrics. And the second is for a given. Now, I choose one of these inequivalent metrics. So for a given inequivalent metric, there exist residual gauge transformations. There exist residual gauge transformations. And so the parameter space, there will be a dimensionality to the parameter space of these residual gauge transformations. And so I'm going to call that K. So each of these residual gauge transformation, it's in the context of string theory, is what's known as conformal Killing vectors. Okay, so those are conformal Killing vectors. All right, guys. So again, so we saw explicitly in the example of this point particle that there is, in our case, there was one moduli and there was one Killing vector. So now when we talk about strings and we consider strings on the topology, some complicated topology of worldsheets, so there is the same issues here, right? So in other words, so this can happen in string theory. And so, in fact, so there is a theorem that can be proven. If I look at the worldsheet, right, of an Euler character chi, right, and so if the Euler character is positive, then the number of conformal Killing vectors is 3 times chi, and the number of moduli is going to be equal to 0. And so the other part of the theorem, when chi is less than 0, so there are no conformal Killing vectors, but there are lots of moduli. Right? So in particular, for example, if I look at genus 2, right? For example, so remember that the simplest topology of a worldsheet for a closed string is a sphere. Then there is a torus. Unfortunately, the torus doesn't go here, right? So T2. So the Euler character is 2 minus 2g, so it's equal to 0 in case of a torus. So it's not being covered by this theorem. But for example, if I go to genus 2, right? So if genus equals 2, so chi equals 2 minus 4 equals minus 2. So in this particular case, a genus 2 Riemann surface, if you ask yourself, so if we believe in this theorem and we ask how many equivalent metrics we can put on a genus 2 surface, right? So this theorem tells us that there is a parameter space of inequivalent metrics, and the dimension of this parameter space is 6. So there is a 6-parameter family of inequivalent metrics on a genus 2 surface. So in principle, this theorem, I'm not going to prove it in class here, but we will discuss it so that it almost will be natural, right, to you. So you will kind of end up, and there is a very nice discussion in Polchinski book, so you can go there and read, and it's very accessible there. So what I want to do now, okay, so this theorem doesn't cover the case, which is simple enough that we can do very carefully in class, and that's torus. So what we're going to discuss now, we're going to look at worldsheets of with the topology of a torus, right? And we ask ourselves, how many moduli do we have, right? How many inequivalent metrics we can put in a torus? So that's the type of problem we're going to solve. And then we're also going to ask the question, how many for each inequivalent metric on the torus, what are the residual gauge transformations that are left? Okay. So good. So is it clear? All right, guys. So I had lots of talks. Okay, so what we're going to do, so let's study in details. We're going to study in details the case that's not covered by this theorem. So this is called Riemann-Roch theorem. Okay, so something that's not covered by that. That's a case. That's a case of a torus. Okay, and so our task, we're going to compute mu. And we're going to compute kappa. Okay, so how do we think about torus? Well, so there are two coordinates. So I'm gonna call them sigma 1 and sigma 2, and I'm going to assume that they range from 0 to 2 pi. Okay, and so much like in the case of the point particle, so we have fields x sigma 1, sigma 2, and then I have g a b of sigma 1, sigma 2, and so so what we're going to assume that those fields are periodic. Upon identifications, sigma 1, sigma 2 plus 2 pi, n and m, where n and m is a bunch of integers. Okay. So we're going to prove now a theorem. So remember that in this case, unlike the point particle case, so now we have our parameterization invariance, right? So we can reparameterize our coordinates sigma 1 and sigma 2. And the second thing that we can do Weyl transformation. So the theorem tells us that by Diffie cross Weyl transformations, any metric on a torus, any metric, and a G2 can be put in the following form. Right, so the metric d squared is going to be absolute value d sigma 1 plus tau d sigma 2 absolute value squared, and this tau is a complex parameter. Okay, so in other words, what the theorem that we're going to prove in a second, we start proving and we finish, it tells us that there is a two-parameter family of inequivalent metrics on a torus. And in fact, any metric on a torus by using diffeomorphism and Weyl transformation, you can put in that particular way, where tau is some complex number. So in particular, in our case, right? So we looked at the worldsheet metrics corresponding to tau equals I. Right? So if tau equals I, then the metric on the worldsheet is just d sigma 1, d sigma 2 is a fact. Okay? Right. Okay? Those things are right, guys. Good. So let's go ahead and let's prove it. Okay, so again, we start with another trigonometric, GAB, sigma 1 and sigma 2. And so generically, this metric will be curved. So there will be the only non-trivial component in Riemann tensor is so the whole Riemann tensor you can write down in dimensions as proportional to a Ricci scalar. So this is the only component. So this in principle is a function of sigma 1 and sigma 2. And in general, if you tell me whatever metric you have, the Ricci scalar for that metric is not equal to 0. So the first things that we're going to do, we're going to make the Weyl transformation, right? GAB will go to e to the 2 omega GAB. And so we know that once we do Weyl transformations, so this is Weyl transformation, will change Ricci scalar, right? So this is something that we discussed some time ago. And so in particular, if I choose my Weyl factor omega to satisfy the following equation, so this is just a Laplacian on a worldsheet, 2 times nabla squared omega equals r, so original r. Then in the Weyl transform metric, it will have zero curvature, right? So it's the Weyl transform metric. We have b equal to 0. Okay. So if you look at, well, if you recall what you know from different partial differential equations, so this equation always has a solution locally, right? So. So this equation, we take that star. So star always has a solution locally. Okay. However, you might worry whether locally is not good enough in principle for us, right? So we want to have this Weyl factor to be defined, well-defined everywhere on the worldsheet, so it must be globally defined. So what are the conditions that it's defined, well-defined globally? So is a condition that omega exists globally. Okay, so let me explain here what the global constraint comes from. So I can take this equation, right, and what I can do, I can multiply by the square root of the metric, right? So this is an integral over T2, number to omega, d2 sigma, right? So what I'm doing, I'm integrating the left-hand side, and so it must be equal to the integral of the right-hand side. Okay? And so, as you will see in a second, that produces a global constraint. The reason being is that what I have here, I have the integral of total derivative on a curved manifold. And so what I can do, I can transform this as an integral over a boundary of a torus, right? And then, so that would be an integral of a normal, unit normal to the boundary times nabla omega. The only problem is that the torus doesn't have a boundary. So what this tells us that this thing must be equal to 0. Okay, so there is no boundary. So here what I'm using is the standard Cauchy's theorem, right? And so in the case of a torus, the left-hand side equals to 0. So you can see that that immediately puts a global constraint, right? So the only way I can find omega globally, only if this integral must be equal to 0 as well. Now here we are lucky, and that's one of the reasons that I choose torus, because what this integral evaluates, a topological feature of the torus. So in particular, what it evaluates, this integral simply evaluates 4 pi times an Euler character. And it just so happened that torus has an Euler character of 0. Okay? So what we are finding that there is no global obstruction to finding a Weil vector that would put a metric on a torus to be flat. Okay, that would make torus fashion. So notice that this would not work for a sphere, it would not work for higher genus surface. But the case of a torus, the ones that we're discussing here, is really special. Okay?
Is it also because torus is actually parallelizable? Because you can, at any point, you can define the 2D flat matching from local. But on sphere, you can't. You always have a singular point on the north pole south.
Yeah, you can. It's probably related, but you know, this is a more general statement, right? So this is a statement about topological properties of the manifold. All right, guys. So what this tells us? This tells us that indeed we find this Weil vector, and now our metric becomes flat, right? So by using these Weil observations. We went from sigma A, we went to sigma A tilde, and so here we had some general metric GAB. So in this case, in the tilde coordinates, our metric is just GAB, it's just delta AB. So we have a unit metric here. But the problem that you have to anticipate, there will be one subtlety, and it's exactly the same subtlety as it was in the case of a point phi. So the subtlety comes with the range of coordinates, right? So what we had before, we had sigma A is identified sigma A plus 2 pi, right? So all our coordinates were periodic with periodicity 2 pi. But now we did while rescaling, so we rescaled the range. And so in general, what would happen is that the periodicity in this new coordinate will change. And so now we will have sigma tilde A plus 2 pi. right? So normally, well, so here I can have, so I can have n and n, right? So different integers for a equals 1 or 2. So here what I can have in general, what will be m times ua plus n times ea, right? So where ua and ea are some fixed vectors, right? But in principle, so they constant, they don't depend on coordinates. So that's what they mean that they are fixed. But they can be, in general, arbitrary, right? So if you start with an arbitrary metric, so then in general you will change periodicity in such a way that instead of being periodic with 2 pi m or 2 pi n, it becomes periodic up to 2 vectors, right? So is this clear? Okay. So so one thing that I want to show is that remember what we were doing in order to go to these coordinates, right? We were solving this Laplace equation with the source on a torus, right? And so I was telling you that there is a solution and there is no global abstraction to finding this solution. But remember that I never said that the solution is unique. Okay? So the solution is not, and the solution is clearly not unique. Because if you tell me that you found one solution to this equation, I will tell you take this omega and add a constant, and it will still be a solution. And so, so what this tells us? This tells us that once we went to these new coordinates, there is still a residual freedom left. So we can preserve all these nice features of having a flat metric. And what we can do, we can still do a constant rescalings, right? We can do a constant rescalings. And what else we can do? We can do a rotations, right? So in other words, so doing rotations of sigma tilde 1, sigma tilde 2 plus rescaling plus rescaling, which is nothing but a shift of omega, right? So what we can do, we can choose this vector UA to be 1, 0. Okay?
It doesn't have to be a constant shift, as long as it satisfies the function equation.
Right. So
It can be a constant.
yes. So, but for the purposes that I'm talking here, what's important for me is that I want to put this vector to some canonical form 1. So for me, for that, it's enough to have it, a constant shift. But you are right. In principle, a Poisson equation on a manifold can have lots of zero modes. All right, guys. So very good. So once we've done that, right? So what we are left with, we are left with an arbitrary vector d sub a. Okay, so we are left with a single complex parameter that I'm going to define as tau equals b1 plus I b2. Right? So I left over arbitrary vector b sub a. Okay. So what I can do, I can do two things, right? So the first thing I can do, I can just say that I introduce a complex coordinate on the worldsheet omega, which is sigma tilde 1 plus phi sigma tilde 2. Okay, and so in this complex coordinate, what will happen is that the matrix is flat. The matrix is flat, so it's just d omega bar, d sigma tilde 1, d sigma tilde 2, up to a factor 1/2 or 2. But if I am staying up here, then what's happening is that I would have to identify my complex coordinate omega, not with 2 pi m plus I 2 pi n, but I would have to identify as 2 pi m plus tau n. Okay, so that's the identification that we have to do. So the way to see this, all you have to do is to substitute what omega is in terms of these two other variables. You substitute what tau is, and you will see that the transformation property will simply reproduce these ones. Sigma 2 plus 2 pi m d2 and sigma tilde 1 plus 2 pi m plus m d1. Okay, so that's one way I do. So notice that what I did here is kind of equivalent to the first case we did in the point particles. So we kept the metric in a canonical form, kind of a unit metric, but the price we paid is that we had to introduce our moduli in the range of parameters, right? So now, our parameters depend on tau. So the second thing that we can do, we can go ahead and we can introduce omega as sigma 1 plus tau sigma 2, okay? And so in this complex coordinate, we have the correct periodicity plus 2 pi m plus n, and so in this coordinate, what will happen that sigma 1 and sigma 2, they are identified as was before. Okay. There is and from that, the period of sigma 1 and sigma 2 was equal to 2 pi. So, and in these coordinates, right, so typically what we will do, and what people discuss, is that they keep coordinate range fixed, right? And so if we do that, then the metric is no longer take a simple form, d sigma 1 times d sigma 2, and so in this case, the metric ds squared becomes just absolute value of this dot. So it's d sigma d sigma 2 value squared. Okay. So that's the end of the equation. All right, guys, so any questions? Okay, so very good. So let's continue discussing. So we found that there is a one parameter family of inequivalent metrics on the torus. And so that parameter is this complex number tau. But the next question we're asking, are we really sure about that? Okay, so we're finding that what we will find out now is that different values of tau, locally there will be one-to-one correspondence between inequivalent metrics and taus, but globally, as we will see in a second, it's not the case. So in other words, different taus will correspond to the same metric. Okay, so let's talk about that. So there is remember, the reason why we go in so much pain is, again, we have to be very careful as we are, once we are setting our class integrals. So we really have to understand very carefully what are our gauge degrees of freedom and what are our inequivalent field configurations. So what I'm saying here is that now, after you did all this discussion, you can happily conclude, well, you know, a space of inequivalent matrix is parameterized by tau, and so in your path integral, what you have to do, you have to integrate over all complex parameters tau. And the problems that you will find out is that the answer will be infinite. Okay? So the answer will be infinite, and the reason for that is because you will end up overcounting the inequivalent metrics. And you will be overcounting it infinitely many times. That's why you will get an infinite answer. So it's tau, which is inside a complex plane. But this is not the case. Not the case. And again, I emphasize we need to figure out what this space is, because when we compute our string path integral, we have to integrate over equivalent metrics. So we have to integrate over d tau 1, d tau 2 like integral. And if we make the statements like this, we'll find out that the answers are continuous. And so we have to discuss this subtly. Okay, so in other words, the question of what are inequivalent. Okay, so now we already know that inequivalent metrics parameterized by tau, but now we ask the question, what are inequivalent? What are inequivalent taus? Okay. So first of all, so tau and tau bar are equivalent. And the reason for that is that if you compute the metric ds squared of tau, it's going to be exactly the same as ds tau bar squared. Right? So remember that we made an agreement with you that we're going to think about an equivalent tori with a fixed coordinate range, sigma 1 and sigma 2 goes from 0 to 2 pi, but the metric is given by this form, and so there is an absolute value there. Now, sigma 1 and sigma 2 are real, so it doesn't really matter whether tau is, whether we substitute tau or tau bar. Okay? So what this tells us that in order to talk about inequivalent tau, we have to restrict the imaginary part of tau any way we want. And so I'm going to restrict it by saying that imaginary tau equals to is positive. So what I did here, I excluded imaginary tau equals to 0. And the reason I did that is because when imaginary tau equals to 0, you can convince yourself that's a trivial exercise to just, well, it's pretty much obvious from the formula, but if you need, you can think more and you'll convince yourself that when imaginary tau equals to 0, the determinant of a Walsh-Heath metric, right, is the one that we got. Okay, so I'm not using tilde here, because the metric will become degenerate in this case. And one further implicit assumption that we are doing when we are evaluating path integrals, we always assume that we integrate over non-singular field configurations. So we have to exclude degenerate cases. And so having imaginary tau equal to 0 corresponds to a degenerate metric on the Walsh. You don't want that. Okay. So our first restriction, okay, Okay, so as you can see that we didn't do much, right? So what we did, we cut the complex plane tau by half. Okay, that's not going to help us because I said that the integral is divergent, so I have to find an infinite ambiguity. And for now, it's just a finite ambiguity. Okay, so we have to work a little bit harder. And so let's do that. And the point here is that there are additional redundancies. Okay. And so I'm going to explain them. So one additional redundancy, which I'm going to introduce as a transformation T. But so this is a transformation. When tau goes to tau prime, which shifts tau by 1 unit. Okay, and a second one, it's a redundancy when tau goes to tau prime, which is -1 over tau. Notice that in this transformation, tau goes to -1 over tau there. I'm still staying in the upper half plane. So how do we see that this transformation produce same tori? Okay, so what we're going to show, that this transformation result in the same tori. Right? So the torus is actually exactly the same. And the way to think about this, well, so remember that our torus, we can think of the torus. So torus is a compact manifold, but I can go on an infinite cover of this torus, and instead of I'm going to think of the torus as a plane. Right? So now I'm thinking of T2 as a complex plane, right? And so omega is coordinate of this complex plane. And so the way how I make a torus, I'm just going to make an identification on this complex plane. So I'm going to say that every point with coordinate omega on a plane is identified with a point omega plus wherever we discover it, plus 2 pi and plus n. Okay? So pictorially, what this means is, so how am I thinking about the torus, right? So I will start with an infinite complex plane, and then I'm saying that, well, there are 2 generating vectors on this plane that identify points, right? So one generating vector is actually 2 pi, right? So I can shift omega by 2 pi. And so this is a vector up here. Okay? And then there is another vector. So meaning that whenever I act with this vector, those 2 points are identified. Okay? But there is another vector that produces identification on this infinite cover operators. And that's this vector 2 pi tau. Okay? I'm just going to draw a vector 2 pi tau. Okay, so it's a complex vector. So in general, it will be some some vector, right? And so the point of this identification is that if I act with this vector, I have to identify points which are orbits with respect to this edge. And so you can see that in this way, I can construct a fundamental domain on a complex plane that corresponds to a torus, right? So any point inside here, once I act with those 2 generating vectors, will move me outside, and will simply produce a copy of the torus, right? This is the same vector machine, right? And so you can see here, so if I can go from here, I can identify the point here by choosing n equals -1. So I keep going on. Here, instead of acting one time with this generating vector, I can act twice. And so I identify those. Okay. So this picture is actually very useful because this picture will tell us, so what are inequivalent tori, right? So the way I think about the torus is a infinite plane, a complex plane, and on that complex plane, I'm making identification with two vectors. So as long as the result of my identification as long as I'm identifying the same point, I'm getting the same torus. Okay? Okay. So the idea here is the point is as long as we are identifying the same momentum on the plane, we get the same torus. Okay? And so now, my task, in order to prove that those transformations S and T produce the same torus, tori, is very simple. All I have to do is to demonstrate that going from tau to tau prime will produce exactly the same identification on a complex homologue plane as tau. Okay, so let's show this. So indeed, so if I have tau, right, so omega, when I'm making identifications with tau, then what I'm doing, I'm identifying omega plus 2 pi and plus tau n. Right? Now, when I identify with tau prime, so what I'm doing omega plus 2 pi, and plus, so here I would have to put tau prime, but our tau prime is tau plus 1. However, I can do a trivial arithmetic here. So I'm just going to write it down as, well, let me put times here. In principle, I'm making identification with some integers n and m here. It simply means how many, just on a given point omega with how many generating vectors I have. Right? So here I will have 2 pi n prime plus m prime, right, plus tau times m prime. Okay, so now you can see that, well, both in this case and in this case, n and m are arbitrary integers, right, positive or negative. And so you can see that what I'm doing exactly the same identification, as long as I'm saying that n prime, n equals n prime plus m prime, and m is going to be equal to m prime. But I'm not putting any restrictions because neither n and m nor the time variables, they are restricted in any way. They can take arbitrary values. So we conclude that tau and tau prime equals tau plus 1 produce the same torus. Okay, is that clear? Okay, good. So the next is S transformation. let me make one more thing. That it will be philosophically easier for you to understand the S transformation. So you are happy that I put primes here, right? So in some sense, I'm thinking that there are two planes, right? I have two different torus. One is a torus with tau, and so I start with a plane. The plane has coordinate omega, and I make this identification, right? And then I have another torus. So I start with another copy of the plane, and I make identification with tau prime. Once I said this works, what I'm saying is that in principle, I have another copy of the plane, so I have another coordinate on that plane. And so strictly speaking, when I'm making this identification, another identification I'm making to make sure that it's exactly the same torus. What I'm saying that I identify point-wise coordinates on one plane with the coordinates on the other. Okay? So that's an important step. It's a trivial thing here, right? You would say, why are you doing that? But that's a step that we will need to do when we discuss identification with respect to S. Okay? So again, the idea is going to be now exactly the same, right? So I'm going to say that I have two planes. So the first plane makes the identification 2 pi m plus n tau. Okay? And then there is another plane, another torus. And so I start with a plane which has coordinate omega prime. And on that omega prime, I'm making the identification m prime plus n prime tau prime. Okay, so the starting point is exactly the same. It's exactly the same as here, right? So this is tau prime. So now I'm verifying whether tau prime equals to -1 over tau will produce me the same torque. So I have to substitute the value of tau prime, which is n divided by tau. Sorry guys, there is a prime here, and there is a prime here. Okay, so on this plane, on the second plane, I'm making this type of identification. It doesn't look like anything similar to this, right? But in fact it is. In order for you to see that it is, what I'm going to do, I'm just going to divide. So this is an identification, right? And omega is an arbitrary point. So what I'm going to do, I'm just going to divide. I'm going to divide both sides by tau. So this is a non-singular operation because remember that the imaginary part of the tau is never 0. So the absolute value of tau can never be 0. So I am happy to do that. So once I did that, so I'm producing a new identification. So this first torus, I can think of it that it identifies the points omega over tau with the points omega over tau plus 2 pi. And then I have n plus n divided by tau. Okay? And now we ask the same question. Is there a simple map between those two transformations so that we can conclude that both tori are the same? And the answer is yes. So the first thing what I have to do, I have to say that omega prime equals omega over tau. And then I'm going to say that n equals to m prime, and m equals to minus m prime. So once I did this map, okay, what I did, I provided a point-like maps between a torus here and a torus here. So I showed that those two tori are equivalent. So what we are saying is that tau and tau prime is -1 over tau produce the same. All right, guys? No questions? All right, guys. So now we know that there are two transformations, two discrete transformations that identify tau. Those are S and T transformation. And then we can ask the question: so what kind of algebraic group the S and T transformation generate? Right. So what's the algebra of these S and T transformations, right? And so in order to understand what's going on, right? So notice that S squared equals to 1. So if I act with the S transformation, then I will get identity, right? And then you can verify that STQ equals to 1, right? So if I act on tau with T transformations, then act on S, and repeat this procedure 3 times, I will get back to tau. So in fact, what you can show that S and T generate what's known as PSL to that group.
S&T mute or?
No, they don't. So no, they don't. It will be very clear how you can think about S and T transformations. So they generate this PSL to that group. Again, the idea is that you have these two generators, and I act on tau in all possible ways, right? So in all possible combinations. So for example, I can start with tau, and I can go to tau prime, which is ST squared, and then ST to the fifth acting on tau, right? So what do I mean by this, right? So first, T to the fifth act on tau, what I'm getting. I'm getting tau plus 5. Then I act with S transformation. So what I'm getting is -1 over tau plus 5, right? Then what do I have to do? I have to act with T squared transformation. So I have to act 2. Right? So up to now, my tau got into 2 minus 1 over tau plus 5. Now I have to act with the S transformation back. So I get -1, 2, -1 over tau plus 5. I'm up to here. So up to here. Then I act with T again, plus 1. Okay? Actually, by doing this example, you can already see what kind of the most general transformation on tau you're doing. And so it turns out that what you are doing by repeating an arbitrary sequences of S and T transformations, or in other words, you ask the question, what group S and T transformation generates? So they generate what's known as PSL to Z group. And so this equals SL to Z model by Z2. So SL to Z as a group of 2x2 matrices, right, with integer entries, right? So these are special linear transformations, right? So that's those special linear transformation acts on the field of integers. So an element of SL to Z is simply a matrix A, B, C, D, such that A, C, D are integers. And also what's going on is that those guys have a unit determinant. And so all these matrices in B, C, have a unit determinant. So I told you what SL to Z is, but I said that PSL to Z is a Z2 orbifold of this group. So I have to specify to you Z2 action. So Z2 action is the action that identifies these integers. Okay. provide this type of identification. And so now, once I map these generators S and T, so now I have to say how does element of SL to PSL to that group act on tau, and the action is given by the following. So tau goes to tau prime, which is A tau plus B over C tau plus C. Okay, and you kind of see the structure emerging as we act with a sequence of S and T transformations. Right? So with this action, you also immediately see why do you need to do this modding by Z2? Because A, B, C, and D, if you change them to the opposite, you are doing nothing to tau prime. Okay?
This is similar to the global group generated by L0 plus.
Yeah. That's a Möbius group, right? Yes. And so actually, you can now ask, so in this language, what are, just to kind of go back to your question, how do I see whether S and T transformations can use or not? And kind of the easier way of sorting out this. So we are mapping the generators, right, into the elements of PSL to that group. And so then I must be able to identify what is my T and S transformations as the element of this group, right? So you can immediately see that what T is, so it's 1, 1, and then I have 0, 1. Okay? So that's your T element. And what's your S element? So the S element is 0, minus 1, and then I have 1, 1 and 0. Right? So most matrices have a determinant 1. And so in fact, you can show that the sequence of action with various generators on tau simply corresponds to a matrix multiplication, right? Okay, and so that also explains you, well, the question, your question becomes a question, does this matrix is convenient or not? Okay. And so another thing is that this group, or these generators have fixed points, right? And so those fixed points are, the ones that are left invariant by a particular combination of S and T transformations, right? And so it's clear that the fixed point is S squared, because if I square this matrix, right? So if I do square, so S squared, then I'm going to get an identity. So I can repeat exactly the same exercise in the case of ST. Okay. And I don't want to do linear algebra here, so I'm just going to tell you. So when you compute, right? So you do ST cubed, and so you will find out that it's minus 1, 0, 0, and minus 1. But it's exactly the same as identity, because that's where this actual modding becomes important. Right? So this is the same as 1, 0, 0, 1 as an element in PSL to Z. Okay, so very good. So what does this tell us? This tells us that actually you can now see that there is a lot of identification that's going on this tau plane, right? And integrating over a whole tau plane is not the right thing to do. For example, just having the T generator, I can restrict the inequivalent metric to be inside this string. So it's from minus 1/2 to 1/2, because any point of tau, and actually we're living in the other half plane, because any point here, if I act with the T transformation, will move me outside. So what I'm doing right now, I'm asking what is the so-called fundamental domain of tau. So I'm finding the region of tau that is left, the smallest region
that does not contain redundancy with respect to this PSL to Z transformation. And so now you can see already where the infinity comes from. Because I have already this strip, and so if I add this T transformation, I can transform it infinitely many times to the left and infinitely many times to the right. So now in my path integral for the string theory, when I compute an integral with respect to tau, at least I have to restrict the integration along the real part of the tau. Right? So what I have here is real part of the tau, and here I have imaginary part of the tau. The real part of the tau can only change from -1/2 to 1/2. Okay? Anything else is just gauge transformation. But that's not the case. That's not always the case because we looked only at the T generator. And then we are left with the S generator. And so if you ask, so if you are living inside here, how does different points transform? Is there any additional redundancy? And the answer to it is yes. And so in fact, the fundamental domain ends up to be the following. It's going to be the strip that goes up to infinity, right? And so this is a unit radius circle. This is just a unit radius circle that intersects the strip. So this point is I, right? So this is a point. This value of tau is, if you wish, so S and T are kind of duality transformation on my modulus parameter tau. And so if I ask, so if I act with my S transformation, right, and so on tau, what in general S will transform tau, right? So we know that for any tau it will go to -1/tau. But I can ask the question, what values of the moduli are self-dual? Which ones are invariant under action of duality transformation? Okay, so in other words, I'm solving this equation. And so here, this point is a solution of this equation, right? So this is this point tau equals I, and you can see it immediately. So I will go to -1/I, which is exactly the same as I. So tau equals I is a self, is S invariant element, right? So S duality invariant modulus. And now you know that. Okay, so I'm telling you something that probably overwhelming you unnecessary. But the point is that there is, if you think more, so this is a fascinating story, and you can just think for yourself what this fundamental domain looks like and how different generators are encoding in the fundamental domain. And so what I want to point out here is that there is an opening angle here. This opening angle is pi, right? And this is an opening angle for the S duality self-dual element. But the S duality, the S transformation is order 2, right? Meaning that if you act twice with it, you get back an identity. So it's always the case that the opening angle around the self-dual element for a particular finite order generator in the group is 2 pi divided by the order, right? So this opening angle pi here, all I'm saying is that it's 2 pi, the full angle of the frame divided by the order of the generator S in the group, right? So by order means that how many times do you have to multiply this generator by itself so that you get back to identity. So the order of S in PSL to Z is 2, so the opening angle is 2 pi divided by 2. And now you can see that there is another special point, right? So those special points are here. And in fact, you can see that
there is some nice opening angle associated with them. So this angle is actually pi over 3. Okay, if you just do the trivial geometry. But in fact, what you have to think is that there is another fundamental domain that is being attached. So the full opening angle around this point is pi over 3 plus 2 pi over 3. And so, this point has an opening angle of 2 pi over 3. And so that suggests that the value of tau corresponding at this point, notice that this point is exactly the same as this, because they identify by a t-generator. So according to what I told you, you might suspect that the value of coupling here must be a self-dual coupling not coupling. Okay, so exactly the same story happens in nice field series, supersymmetric field series, and so the same kind of transformation show up. Okay, so exactly the same modulus must be, so this modulus must be a self-dual modulus with respect to an element of what is 3, right? A generator of what is 3 in the group. And we already discussed that there is a generator of this type, and that's this ST generator, right? So remember that ST cube equals to 1, right? So there is this ST, and so the value of coupling here is the value of modulus here. So this is a self dual modulus. On the ST transformations. So again here, ST in terms of matrices is given by this. Corresponds to this matrix. And so in order to find out what is the value here, what you have to do, again, you have to solve this equation. And you will get the number from, you will get the number that comes through. All right, guys, so any questions? So the bottom line is that once we have a worldsheet with the topology of the torus, we cannot identify all possible metrics. We can identify all, there will be a leftover physically inequivalent matrix. They will be parameterized by tau, and the tau is not any complex number, but an inequivalent taus live in this fundamental domain of TSL to Z. All right, so let's talk about the other aspect. So for now, what we computed is the number of moduli for a torus equals to 2. And we have to finish the discussion by asking are there any unfixed diffeomorphism transformations, and the answer is yes. And they are kind of very trivial to understand, so we'll talk about conformal Philly group. For torus. And so here, it's really obvious what they are, because the torus is just a direct product of two circles. And so a conformal Killing group on a circle is just a shift. Right? So here we just have two circles. And so we can shift the coordinate sigma A by an arbitrary vector plus dA. So those are rigid shifts. And so, so in this case, so those rigid shifts, so they will leave periodicity unchanged, they will leave our metric unchanged, and so those are the residual gauge symmetries. So what we are finding is that kappa, in case of the torus, equals to 2. Right, so I already mentioned to you that how do we deal with modular, right? So because modular correspond to inequivalent configurations, we have to integrate over all possible modular when we compute our path integral. But what do we do? What do we do with this conformal killing group? What do we do with residual transformation? And the answer is that when we compute the correlation functions, right? So we insert vertex operators at different points on the world sheet. And so the idea here is that we can use this residual gauge symmetry in order to fix the insertions of vertex operators at a particular point on the world sheet. So in computing correlation functions, correlation function or S matrix elements, this conformal killing group symmetry, right, can be used to fix position of some operators at a particular point. Can be used to fix position of some vertex operators. Right. So in particular, what this tells you, remember that when we insert a vertex operator in our path integral, what we were always doing, we were integrating over the insertion, right? And so now we have to be much more careful in the presence and pretty much redo all this discussion that we have been so cavalier. I'm just giving you a glimpse. The story is much more complicated than what we did. So, in fact, the fact that we have this conformal, leftover conformal killing vectors tells us that for certain number of vectors, we don't have to integrate, but we have to, we are free to pick them at any position we choose. Kind of similar things that we do in the case of integral over all possible metrics, right? So we have to choose a corresponding orbit which intersects each gauge slice once. So, so in the case of a torus, because we have two conformal killing vectors, right? Okay, so we have k equals 2, so we have two parameters. So what this tells us? This tells us that on the torus, I can use this residual CKG symmetry in order to fix one vertex operator to be at a particular point on the torus. But whatever, if I have a scattering, say, of five string states, right? So I will fix the position of one vertex operator using this group, and then I have to integrate over the arbitrary insertion points of the remaining 4 vertex operators. Okay, so that's the way how. And so Joe Polchinski in his book, he goes into quite some details, precisely what type of things you have to do to have a well-defined path integral, taking care of the moduli and taking care of conformal killing group. But unfortunately, I don't have time to talk in the class here. All right, guys. So what we're going to do, let's have about 5-minute break, and after the break, we'll talk a little bit about tree level amplitudes.